Hello and welcome to RF Design Tutorials. This is tutorial 19 on constraints-based RF circuit design. What you will learn in next few minutes is how to design your circuits as per board real estate and BOM constraints. And to illustrate the concept, I have taken an example of a fixed topology impedance matching network calculation techniques. You would imagine in the real board design, often a time designer do not have all the flexibility and freedom to come up with his own, matching network topology or circuit topology, and often he has to constrain himself or herself into the available, real estate or the topology which is already laid out on the board. Like shown in this picture, I have two chips to match and I only have these four components which you can use to do impedance matching. However, even if you have four components available, you're trying to look for a way to minimize the bill of material to save some cost. So we will look at some of these techniques which we can use very easily inside ADS to come up with these circuit design despite being in a certain constraint based environment. Also, we will look at data access component, which is a very versatile component inside ADS, allowing you a lot of freedom to read in any format of files and use in your circuit design. And during this course, we will also learn how to sweep the S2P files and then how to optimize the circuit design while using S2P files, which is not very easy thing to do, but you will see how easy it is inside ADS to optimize your circuits, even if you have bunch of S2P files for components. Now, before we begin, subscribe to my channel. Once you subscribe, don't forget to hit the bell icon to enable all the notifications. And after you watch the video, don't forget to give it a thumbs up and share it with your friends and colleagues who may be interested in watching a similar tutorial. All right, let's get started talking about each of these topics in a little more detail. So here to illustrate the concept, I have divided my tutorial into two parts. We will first look at how can I use traditional parameter sweeps to deal with the constraints which we have in place to do our circuit design. So in option number one, I have a very simple pi topology, which currently is like a low pass topology, and I have set up a nested parameter sweep. I already created a previous tutorial video talking about parameter sweeps and nested parameter sweep. So feel free to see that video if you're not very comfortable setting up the nested parameter sweep. So here in nutshell, let me give you a quick glimpse of what I have done. I have defined a parameter sweep for C1 value, which is the first shunt capacitor, and it is going to sweep from certain range to certain range. And then this sweep will call another parameter sweep, which is set for C2, which is the second shunt component, and which in turn will call L1, and then finally the S parameter on the desired frequency on which we would like to analyze. So this is a simple nested parameter sweep concept inside ADS to do all permutation and combination. Now, traditionally, when you deal with parameter sweep, which you can obviously obtain by going to any simulation library palette, and from here you bring out the parameter sweep. And by default, the way it is set up, you can define the parameter value name, which you have to sweep, define the sweep type to be linear, log, or single point. Now this works in most of cases, but what if I do not have a continuously or a linearly changing value of the component available for my circuit design because I have a fixed inventory, I have few specific values to select from, and I need to see what best impedances can be obtained with a certain topology in my network. Well, precisely that job can be done if we don't define the sweep value or sweep range in the parameter sweep. So instead, here you can see I have activated a sweep plan and I have linked this parameter sweep to this sweep plan 1. And this sweep plan again is the component which you can obtain from any simulation library palette here. So in this case, the way I have declared the sweep plan is for 1 to 5. I have defined a linear sweep with the increment of 0.2. Let's say those are the values I have available. And then I have added few single points for the fixed value which I have available in the inventory, and they are not constant or they can be totally arbitrary, right? So that's how my parameter sweep is going to change the values of C1 and C2, because both of them are referring to sweep plan 1, because both of them are capacitors. Similarly, for inductor, I do have another sweep plan, and here you can see I have defined the values from 1 to 10 in the increment of zero point 0.5. Yeah, I know they not all values are standard values, but I'm here illustrating the concept. And then I have few discrete values of 22, 24, and 27. And the units are declared in those respective components. So capacitors are in picofarad and inductor is in nanohenry. So once I run the simulation, at the end of simulation, what I can do is to plot S11, which basically will give me the impedances which can be realized using that particular pi topology within the given value constraint. And here you can place marker at any location. At that location, you can see the impedance and the component value combinations, which is able to give you that particular impedance on the Smith chart. So now if you have any impedance, information which you need to match at a specific frequency, you don't need to run optimization and go through those laborious steps to do your circuit design. Simply look up on the Smith chart, place your marker near to that impedance, and you have the values available. So this is like a way, in a way, is a lookup, based approach to come up with your desired impedance matching network. So if you want to see it on any other frequency, for example, if you want to see the performance at 1 gigahertz, you just go ahead and change the frequency to 1. The rest of the constraint remain the same. And now you have different set of impedances which can be obtained or which can be realized using that matching network within the values available. Cool, right? Okay, so that's step number 1. Similarly, like I have come up with this low pass topology, you can also come up with a high pass topology for similar circuit. Rest of the process remains the same. And with this high pass topology, you can look at a different set of impedances which you can obtain. So depending upon what impedance you have to achieve, one or the other topology will work better, or sometimes you can achieve the same impedance with both of those topologies. Then you can make your decision based on the value of components which you need in order to achieve that impedance. So choice is up to designer. So this is one kind of constraints based circuit design. In option number 3, we can be a little more innovative, and that's the beauty of ADS, is allows you to be as innovative as you want. So in my case here, I have set up combination of inductor and capacitors preceded on either side by a switch. Now this is like an ideal switch which will have a 0 dB loss, 1 VSWR and 1000 dB isolation. That means it is not going to affect your circuit performance in any way. By choosing the right state variable, my signal will either go through this inductor or it will go through the capacitor based on what I set as state. And here I have declared a variable called switch state. Similarly, on either side as a shunt, I have a couple of switches and inductor and capacitor combination. And here, the way I have set up this state variable to be different or inverse of what you are going to do here. For example, if you decide to connect to inductor, which you will get once this switch state is set to 0, I have declared another variable here, which is going to create the different state for the shunt side. So in this switch is either 0 or 1. So if the series switch is set to 0, the shunt will set to 1. That means I'm going to pick capacitor for my shunt. So it will become a low pass topology. When my switch state is set to 1, that means I'm picking up the capacitor. The state here will set to 0. That means I will pick the inductor in the shunt. So this way I can run a bunch of parameter sweep. The top row is basically in the low pass topology, and the bottom sweep will be performed for the capacitor topology. And here I have a master parameter sweep which is going to sweep the switch state to 0 and 1, So here you can see start 0, stop 1 with 1. And this parameter sweep is going to call sweep 1, which will initiate the sequence of this nested sweep. One sweep, then the third, second, and the third sweep, and eventually leading to the S parameter calculation. And the second sweep is going to call this sweep 4, which in turn will initiate this chain ending at S parameter. So the results which I'm going to get is sweep 3.S11 basically for looking at the low pass topology, and sweep 6.S11 for looking at the high pass topology. So once we have this kind of template set up, we go ahead and simulate our design. It will run through all the possible value permutation combination, giving you two Smith charts, which you will see in a moment. So on the left hand side, these are the impedances which we can obtain at a specific frequency if we choose an LPF pi topology. And these are the impedances which can be obtained by choosing the high pass pi topology. And again, by placing markers, as you can see, they are placed very close to each other. You can see the values combination, which is going to give you that impedance in a specific topology. And you can see both of them are different, although we are achieving a pretty close impedance as we were looking for. All right. So interesting enough. So I hope this kind of concept is going to help you when you want a dynamic topology to meet different kind of requirements for your circuit design. So something new if you haven't tried this already. So something innovative, something new you could try in your circuit designs. All right, so now let's turn our attention to second way of doing, and that is to use a DAC component in ADS. Now, this is not digital to analog converter. This is data access component. And this is a pretty neat concept in ADS. So using DAC, and first of all, how do you find DAC? Well, in the library parts browser, just type data and you get this component here called data access component, which you can place on a schematic. Now this data access component can read in variety of file formats. It could be a discrete value file, an MDIF file, touchstone file, a data set, or variety other formats which are available from different tools or different instruments. So using this DAC component, you can read in any file. As you can see here, I have three DAC components. One DAC component is calling a C value text file, which is containing the available capacitor values. The other two DAC components are calling the same file. Basically, this is for inductor values. And I do have a pi topology, and this is like a high pass, pi topology I have. And instead of declaring the component values directly, I'm reading the values which are available in a specific DAC component. And then I'm passing that value here. And once I sweep the index, it will step through the rows of the file, keep reading new values and keep passing these components, those new values. Because sometime, like I showed you previously, I was sweeping the value of the components from parameter sweep. But what if your list dynamically changes every day, and then you got to update your parameter sweep all the time, and sometimes you can lose track. So it's not very convenient. So instead, a straightforward way could be to come up with a CSV or a text file which is described in a specific format, which I'm going to show you. And it's a very simple format. And as long as you can keep your inventory in that text file, you can directly use it in your circuit design. So let's look at the format of that file. So here under my data directory of this workspace, I do have two files. You can see C and L values. And if I open up one of those files in Notepad editor, you can see the format. It's pretty simple because a discrete value file. I have a header here called begin DSCR data, and then I have a footer end. So this marks the beginning of the file, that marks the end of the file. And then I have a column syntax. So percentage is a variable declaration. The first column is called index, the second column is called L underscore value. And as I step through these indexes, this file is able to give me different values for this variable L value. And this is what I'm going to use in my circuit design. Pretty simple to understand, right? And this list can be expanded at any point of time you want, or reduced at any point of time if you run out of any specific components. And it need not to be in sequence. You can have, higher value defined first, lower value defined second, doesn't matter. It's just the discrete value. Similarly, I also have a C value file which is very similar to L value in this case. And again, both of these files, you can see I have 15, but one file can be 15, another file can be 30. Doesn't matter. They don't need to be equal. They can be completely unequal. All right. So these two files are getting read inside our ADS. So how are we reading these files? Simply double clicking, browsing to that file, declaring the file type as discrete, and under independent variable, I can define the variable name, and this @ sign is the kind of pointer. And I'm declaring a variable name as well, because the first column is only index. So I really don't need to have any variable name. The value of that variable, whatever I read from the file, which in turn will get passed to a variable which I have defined in the schematic. And in this case, it is C index. All right. Similarly, for this file, I am passing the value, whatever I read in L1 index. And for the third, I'm passing this value to an L2 index. So what is the C index, L1 and L2 index? Well, they are simple variables here, and I initialized with 1, 1, 1. So those are the variables which basically will read or get the information from these files. Now, how do I know the size of this file? Because ultimately, I have to sweep this parameter, right? C index. I have to step through each row in this file. So I'm sweeping C index or L1 index. So I have to start. So array always starts from 0, and I have to stop at some place. So that means I need to know how many entries are there in the file. So how many entries are between this percentage sign and the end of the file. So you can always open the file manually and read it, but that's not very convenient, especially if your files are dynamically going to change over time. So here, instead, I can use a simple functions, which can be used with DAC, and the function is get underscore max underscore points. Define the DAC name, so DAC1 and DAC2, because here DAC2 and 3 are referring to the same file. So any length of the file which you can get from DAC2 is going to be same as DAC3. But these capacitor and inductor value files could be different. So I had declared this variable here, DAC1 dot underscore 3 comma 1. So that's the syntax that gives you the maximum points available in the file, and that I'm assigning to a variable X and another to variable Y. And simply in the parameter sweep, I'm starting from 0, so stopping at X minus 1, because that's to maintain the overall size of the file. So in our case, it goes from 0 to 14, because I do have a 15 entries here, right? So all these things, once put in place in ADS, and that becomes pretty regular. Now, how do we define this kind of syntax in any component? For example, if I place a C or a capacitor here, right? So usually we already directly declare the value of the component, but how do I get this syntax? Well, here in the parameter entry mode, instead of using a standard entry, I can define it to be a file-based entry. And now I can link this component to any DAC, for example, DAC1, which is reading the capacitor list file, and the dependent file value name. Remember, the value or the variable name used inside the component is C value, and then the unit I can declare as picofarad. And as soon as I do that, you can see the capacitor syntax will change like this. Now ADS knows you would like to read the value of this component from a file which is getting read by DAC1 component, And in that file, you have a C value variable, which is nothing but the header of this column, which you are going to read. Similarly, you can have more data. You can have Q, you can have ESR, and so on and so forth. And accordingly, you can read in all the values to pass to this component. So that's how simple it is. And now when I run this parameter sweep, ADS will run through, open this file, run through various indexes in the file, and eventually using that file you will have all the impedances which can be realized with the combination of values, and you can look at the index numbers of that file. Each index is representing a certain value and the impedance offered by that combination. Isn't it cool? So this way you can just sweep your S parameter files for whatever purpose you are looking at. All right, so that's one approach. That's how you use DAC for a typical, circuit design. Now let's turn our attention to understand how can we do this kind of constraint-based, let's say, impedance matching network. For example, on my board, I only had a pi topology available, and I only have bunch of S parameter files from my manufacturer. It could be Coilcraft, Murata, ATC, DieCap, any vendor, and I have bunch of S parameter files from them. And here you can see I have set up very similar concept. Instead of inductor capacitor, I have used an S2P file component, and very similar to how do we define inductor capacitor. Once I place an S2P component, instead of directly using a network parameter file name and browsing to a file, I can change mode to file based. And again, you see very similar concept. DAC1, I know which file I'm referring to, and I can define the dependent parameter name or the column name. For example, I could have a variable called SMT underscore file, and that's how this S2P component will change. And that's precisely what's happening here. So let's see what's inside that file. What am I calling in SMT underscore list.txt? Now, another thing which I have done here, I would like this component not to be restricted as a low pass or as a high pass network. So instead of maintaining one set of file for capacitor, one set of file for inductor, rather what I did in this case is mix all those S parameter files listing under a single file. So here under SMT list, if I open that in Notepad, you can see I have a same header and a footer like I used to have earlier. And the column name, the first column is index, the second column is SMT underscore file. That's the variable. And at every index, you can see I have a different set or different S2P file name defined. And all these S2P files are available inside my data folder. So here you can see these are the inductor S2P files. These are the capacitor S2P files. So all of them are placed inside my data folder. And it's not necessary that it has to be inside data folder, but this file and the rest of this parameter file ideally should be in the same data folder. Otherwise, you will have to give a full path here in case they are not at the same location. Anyway, so the first 9 index, as you can see, are belonging to the inductor, and remaining 9 files are corresponding to capacitors. So this in turn will create all kind of permutation and combination because I threw everything inside a single file. That means the S2P component which I have in place on a schematic are no longer only inductor, only capacitor. Once I sweep through, as you can see here, I have 3 parameter sweeps, and again, they are nested sweeps. So this is calling sweep 2, sweep 2 is calling sweep 1, and they are simply sweeping the index of the file from 0 to x minus 1, where x is nothing but the length or the total number of entries in the DAC file. So now let's see what happens. When we run this analysis, all 18 cross 18 cross 18 combinations will be run. And these are the S11 plot which you can obtain, or each point is basically representing certain impedance. And based on marker where you place, I have written a small bit of post-processing equations to compute what index, wherever you place marker is corresponding to certain index. That means file index 1, file index 2, file index 3. At that index, what is the series component value name, which I am obtaining by using this array operation? What's the shunt S parameter file name? What's the second shunt S parameter file name? And here you can see this series component is a capacitor. The second shunt component is a capacitor, but the first shunt component is an inductor. Isn't it cool? So it's no longer only low pass or high pass topology. It could be mix and match depending upon what impedance you're trying to achieve. At that location, using that combination of file, you also can look at S21, which is the loss of your matching network at the frequency of your simulation, which in my case is 2.4 gigahertz. Cool enough, right? So with no effort, basically you can just place a marker. If this is the impedance you need, you know which components needs to be mounted where in your PCB, and that's it. No need for optimization, no need to break your head. All right. Hopefully this is cool enough for you to put it in practice and try it out on your own designs. Now, finally, if you still want to do circuit optimization, so let me first close all the design. If you still want to use a bunch of S2P files and want to do your circuit optimization, well, that's purely possible. So in that case, I do not need to do any parameter sweep. So here, rest of the circuit is still the same. Here you can see I'm still calling SMT a list file, and I'm sweeping or referring to that index. Now these index variables have been made optimizable, and the way I have made optimizable is by using a discrete logic, and I need to constrain myself depending upon how many entries I have in the file. So in my case is 0 to 17 because I do have an 18 entries here. So I have 18 S parameter files available, and the index will change by 1 because the row increment or the index increment is happening by 1. So you already know how to make any parameter optimizable by going to simulation variable setup. Under optimization, I have defined max, min, and step. By default, it will be like min and max, but this is not advisable when you're dealing with discrete data. You should always go with max, min, and step, and make sure you are stepping in the same increment as you have data available. All right, with this simple stuff, I do have my variable, which is going to be my optimization goal. And you can define what impedance are you trying to achieve. And that impedance, it becomes your goal because you are having an S11. You convert S to Z, that means get a Z parameter out of it. And the real part you equate to the real Z, which is this variable, and the imaginary equates to imaginary. And the way you have set up goal is equal to. So that's the target impedance I'm trying to achieve. And in terms of optimization, remember you are switching between discrete values. So the optimizer ideally should be either discrete or random. You cannot use gradient and some other optimizers here, either random or discrete. As simple as that. And once you have this set up, you give it a run of optimization. And now ADS optimization will go and perform simulation. Now, before I run optimization, let me stop optimization. And I don't want to update my values, but before we do that, let me show you. So with the current set of values, I have some arbitrary values set up here. Let's say, let me set everything to 111. That means everything is referring to the same inductor value. Remember, the inductor was the first value in our list. So if I go ahead and run the simulation only, you can see this is where you are. This cross is representing what's the S11 of your current circuit. And target Z is the dot where you have to be. That's 10 minus J10 point. So you can see with the current setup, you have 1 nanohenry, 1 nanohenry, 1 nanohenry, as we predicted, because the first entry in the file is like that. Now, if we run optimization, let's see what our optimizer does. So it will You can see it is sweeping through indexes of different components and it is trying to meet your goal. At a certain point, the iteration limit is reached and you can see the error function, which is 0.0005. That means you're very close to your goal. And if you like to accept it, click close, update your design. And now in the schema, in the data display, you can see both of those cross and dots are coinciding. And if we normalize this readout of marker to 50 ohm, we can see we achieved 9.9 minus J9.7 and our target was J10 minus J10, and the components which are giving us the desired results are these, and that's the configuration and thus the insertion loss of your matching network at that frequency using these components. And again, this is too bad, but I have just picked up some of these SNP files at random. If you have a good SNP files which you're going to use, probably you will have much better response than I did. Now, while our circuit is already optimized, I'm getting the response. So let's say if I want to change, I want to go from 5 plus J5. And if you just run a regular simulation, let's see how far we are. So that's where our circuit is. That's where we want to go. So if you have these two targets, and if I go ahead and run an optimization, let's see how well job we can do in order to reach that number. And again, it's running all permutation combination, and eventually your error function is 0.01. That means you're kind of close. So let's go ahead and update our design and read the here. So you're pretty close, 5.2 plus J4.3. And these are the component values which are giving you the desired response. So that's all for this video. I hope you saw something very new, something very innovative, which is going to help you a lot when you deal with your actual real world circuit designs using ADS. And I hope you agree ADS is a lot of fun to bring out all the innovations inside you. And you can just implement your thought process and come up with the right set of design within the practical design constraints which you have, either in terms of using a fixed topology or restricting your design with a certain list of inventory values which you have in stock to perform your circuit assembly or the PCB assembly. So thanks again for watching this tutorial. And don't forget to give it a thumbs up and put in your good comments in the comment section below this video, and see you in my next tutorial video. Wish you a very happy designing phase, my friends.